Is my slide visible? Please respond whether my slides are visible or not.
Yes, sir. Yes, sir.
Okay, thank you. So, good afternoon to all of you. So, let me start from where we have left in the last class. So, if you remember, in the last class, we were solving the problem of truss, finite element modeling of truss. And in the last class we have seen that how we have generated the elemental stiffness matrix for the entire truss member. So this was the elemental stiffness matrix for the first element. This is the elemental stiffness matrix for second element. This is your elemental stiffness matrix for third element, and this is your elemental stiffness matrix for fourth element. This is part A of the question. Next part is, if you read the question in the second part, what you need to find out, you have to assemble the structural stiffness matrix for the entire truss. I repeat, you have to assemble the structural stiffness matrix for the entire truss. That means for the entire truss, what is your stiffness matrix? And that stiffness matrix, we call it as a global stiffness matrix. I repeat, that stiffness matrix, we call it as global stiffness matrix. How we can get the global stiffness matrix? If I add the elemental stiffness matrix of each and every element of the stress, then I can get finally the global stiffness matrix. So if say global stiffness matrix is denoted by K, then this K will be equal to K1 plus K2 plus K3 plus K4. Okay, that is vector summation of K1 plus K2 plus K3 plus K4. So if you add all these four elemental stiffness matrix, you will get one big global stiffness matrix. Now, what will be the order of the global stiffness matrix? Since I know that the order of any stiffness matrix depend upon the degree of freedom present in the entire structure. So since we are talking about the global stiffness matrix, so we will talk about the degree of freedom of the entire truss structure. We can see that the entire truss structure is subjected to total 8 degree of freedom. 2 degree of freedom along x and y axis. For example, if I talk about node number 1, degree of freedom along x axis is q1, along y axis is q2. If I talk about node number 2, along x axis degree of freedom is q3, and along y axis degree of freedom is q4, and so on. So by looking at the diagram, that means I can say that there are in altogether 8 degree of freedom. That means the size of the global stiffness matrix will be a 8 cross 8 matrix, 8 rows and 8 columns. 8 rows represents 8 degrees of freedom, and 8 column also represents the 8 degree of freedom. For example, say I want to find out, say, this particular value. This particular value is what? 1 1. That means intersection of row 1 and column 1 will be this value. So let us find out from each and every equation where is 1 1. So I can see that this is your 1 1 from the elemental stiffness matrix of element number 1. For element number 2 it is not present. For element number 3 it is present. That is, you can see, that is 0.64. That means 0.64 plus 1. Then for element number 4 it is not present, so 0.64 plus 1 is 1.64. Fine. Likewise, here I have taken some, I have done some calculations, and I have taken something common, and then I am getting this value. So if you will add add all these rows and columns of the element and take some values common, then finally you will get this matrix. Likewise, say if I want to find out the value of, say, this particular element value I want to find out, that means this is what, this is fifth row and fifth column. So I have to find out from each and every elemental stiffness matrix whether fifth row and fifth column is present or not. For first element, there is no fifth row and fifth column, so I won't take. For the second element, yes, fifth row and fifth column is present and the value is 0. For the third element, fifth row and fifth row is present and the value is 0.64, so it is 0 plus 0.64. And for fourth element, again fifth row and fifth column is present, that is 1, that means 0 plus 0.64 plus 1. And after that you take some values common and solve it. If you do like this, finally you will get this 8 cross 8 stiffness matrix. Take something common and at last you will get this 8 cross 8 stiffness matrix. So this is the second part of this problem. That is, you have to find out the structural stiffness matrix for the given truss member, that is the entire global stiffness matrix. Is there any kind of doubt? कोई doubt है?
No, sir, no, sir.
Okay. So you please just solve it. I have just told you the process, how you have to do it. So just solve it and then you can get all these values. Okay. Okay, fine. So what is the third part of the problem? Third part of the problem is using elimination approach. You need to solve for nodal displacement. That means I want to find out what? I want to find out nodal displacements. In altogether, there are 4 nodes present in this particular truss member, and this Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8 are nothing but nodal displacement at corresponding node. That means each node is subjected to two type of displacement, one displacement along x-axis, another displacement of along y-axis. So in the third part of the problem, I need to find out these values: q1, q2, q3, q4, q5, q6, q7 and q8, because these are nothing but the nodal displacement. So let us find out. So before finding out the nodal displacement values, I have to write down the algebraic global equation for this truss element. If you see the entire truss member is composed of several 1D bar element, and for 1D bar element the governing algebraic equation is nothing but the spring equation, restoring force equation. F is equal to k into x, where k is your stiffness matrix, f is your force vector and x is your displacement vector. So similarly, for this entire truss member, the global algebraic governing algebraic equation is k into q is equal to f, where k is your global stiffness matrix, which you have determined in the second part of the problem, that is this matrix, into q. In altogether there are 8 nodal displacements are present, so this q will be 8 cross 1 matrix. 8 cross 1 matrix, that means q1, q2, q3, likewise till q8. This will be the value of this q. And what is this force F? This is global force vector for the entire truss member. Fine. So since displacement are taking place along x and y direction, so let us assume that both due to nodal joint, both this node can displace along x as well as along y direction. So each node will have two components. So in altogether, this force vector will also have two components. Then if it will have two components, then the force vector which I will get is 8 cross 1 matrix. That is F1, F2, F3, likewise till F8. That means K matrix is nothing but your this matrix into Q matrix is this matrix equal to F matrix is this matrix. Is it clear? Any doubt so far?
No, sir, no doubt.
Okay. So before writing this entire governing algebraic equation in equation for the entire truss member, let us find out whether any boundary condition is present in the problem or not. Whether any boundary condition is present in the problem or not. For that, let us see the problem. I can see that the first node and the fourth node is fixed. If the first and the fourth node is fixed, that means first and fourth node will not displace neither in x direction nor in y direction. That means the values of q1, q2, q7, q8 is 0. Is it clear?
Yes, sir.
Fine. Since it is fixed, so node 1 and node 4 will neither displace along x-axis nor it will displace along y-axis. That means q1, q2, q7, q8, which are corresponding nodal displacement values, those will be 0. And if you see at node number 2, this node number 2 is also fixed. In the problem, it is like this. I have not shown over here, but you can correct it. This, if you see this node number 2, it is fixed. But if you see node number 2 carefully, one force is acting at node number 2 along positive global x-axis. That is how much? 20,000 Newton. If this is the case, then displacement along y-axis is 0, because if this second node is fixed, fine, and it is
The
displacing.
Q3 will be not 0.
Yes, q3 will not be 0. I will get some value of q3, but q4 is 0. But if you see node 1 and node 1 and node 4 are completely fixed. That means you can say that it is attached with a wall. If that is the case, then both q1, q2, q7, q8 is 0. But if you see the problem at node number 2, tensile load of 20,000 Newton is applied at node number 2. So what will happen? This node will have displacement along your x-axis, but due to this fixed support, it will not have displacement along y-axis. That means q4 is 0. So what are the boundary conditions which we have got from the problem? That is q1, q2, q7, q8 and q4 is 0. And if q1, q2, q7, q8 and q3, q4 is 0, fine, you can check this global stiffness matrix. This 1, 2, 3, 4, 5, 6, 7, 8 are now are nothing but the corresponding rows and column corresponding to your degree of freedom. So if q1, q2, q7, q8 and q4 is 0, corresponding row and column you have to eliminate, because that is the elimination approach. Yes or no? I have to eliminate
Yes, sir.
column.
Yes.
I have to eliminate row 1, row 2, row 7, row 8, row 4, as well as column 1, column 2, column 7, column 8 and column 4. This is the matrix elimination approach. So if you eliminate all these rows and column, finally you will be left with 3 rows and 3 columns, and those 3 rows and those 3 columns are row number 3, row number 5, row number 6, column number 3, column number 5 and column number 6. That means along 3 you will get displacement q3, along 5 you will get displacement q5, and along 6 you will get displacement q6. So the resulting matrix, this k matrix, from this k matrix eliminate all those rows and columns. So which row and column you have to take? You have to consider 3, 5 and 6. The this value is same as it is, that is 29.5 into 10 to the power 6 by 600 into 3 by 3 matrix. Which 3 by 3 matrix? Third row, fifth row, sixth row, third column, fifth column, sixth column into 3 by 1 nodal displacement vector matrix. Along third row and third column you will get displacement q3. For fifth row and fifth column we will get displacement q5. For sixth row and sixth column we will get displacement q6, which is equal to along third nodal point, what is the force? For fifth nodal point, what is the force given in the problem? For sixth nodal point, what is the force? For that we have to see the problem once again. That is along third nodal point, I can see that a force is acting along positive x direction. That is how much? 20,000 Newton. So value of F3 will be plus 20,000. Okay. along node 5. So at node 5, at node number, sorry,
minus 25,000 Newton.
yes, I can see that at node number 3, at node number 3, load acting is how much? That is minus 25,000 Newton in negative y direction. So this value, which value? That is this value will be along node number 6. See, if you see node number 3, displacement is q6 in y-axis, global y, and q5 in global x-axis. And since at node number 3, force is acting in negative y direction, that is minus 25,000 Newton. So I have to write that particular value along the sixth degree of freedom, because for sixth degree of freedom, load is how much? Minus 25,000 Newton. So along row 6 or column 6, this particular value will be minus 25,000 Newton. Is it clear?
Yes, sir.
Fine. But if I see the fifth degree of freedom, if I see the fifth degree of freedom, fine. In the along fifth degree of freedom, is there any external load is acting at this particular nodal point 3? Any external force is acting at node point at nodal point 3 for the fifth degree of freedom?
No, sir.
That means I have to assume that particular force along that particular degree of freedom to be 0. That means along the fifth row or fifth column, this value of force is 0. This value of force is 0. If you solve this matrix equation, you are having 3 unknowns, you will get 3 equations. Solve these 3 equations and get the value of nodal displacement q3, q5, and q6. That means, say, if I talk about q3, so for that what I will do, this is matrix multiplication, this row with this column, that is 15 into q3 plus 0 into q5 plus 0 into q6 is equal to 20,000. Okay, then that means 29.5 into 10 to the power 6 by 600 in bracket 15 q3 plus 0 into q5 plus 0 into q6 equal to 20,000. Second equation will be when you will multiply this particular row again with this particular column, that means 0 into q3 plus 22.68 into q5 plus 5.76 into q6 whole bracket 29.5 into 10 to the power 6 by 600 equal to 0. Likewise, you will get in altogether 3 equations. Solve these 3 equations, you will get the value of q3, q5, and q6, which is this particular value. So finally, the nodal displacement for the entire truss member, I can write it as Q, that is global nodal force vector is nothing but Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8. By boundary condition, already Q1, Q2, Q4, Q7, and Q8 is 0. And by elimination approach, I get Q3, Q5, and Q6. So this is the third part of your problem, solution of the third part of the problem. Is it clear? Any doubt so far?
Yes, sir. Clear.
Okay. Okay. So just wait. Okay, fine. Next part of the problem, that is the fourth part of the problem. Again, let me go back to the question. The fourth part of the problem is what? You have to recover the stresses in each element. That means in each element, you have to find out what is the stress value retained by the element due to application of 25,000 Newton load at this particular node and 20,000 Newton load at this particular node.
सर यहाँ पे नोट जो ये 20,000 लग रहा है न्यूटन वहाँ
Huh?
पे तो कोई फिक्स्ड नहीं है वो.
No. That is given in the question. I forgot to tell you that that fixed support is along y direction. This is that fixed support. I
Okay, sir.
forgot to tell you.
Okay, sir.
It is
Okay,
there.
sir.
Okay, fine.
Okay, sir.
So if I want to find out the elemental stresses, here I can see the total one, two, three, four. Four elements are there. Already in some previous, in some one or two class back, we have derived the elemental stiffness matrix for a truss member. So we will use that matrix equation for elemental truss for finding out the value of the elemental truss, and we will find out the stresses in each member. So I know that the stress in any truss member is given by sigma is equal to E suffix small e, that is modulus of elasticity of the element, divided by L suffix small e, that is equivalent length of the element, 1 cross 4 matrix minus L minus M, L M, where L is your cos theta, M is your sin theta, into global Q matrix. Q is your global nodal displacement vector. So if I talk about if I want, I am interested in finding out this stress value for element number 1, then for element number 1 I have to substitute the value of elemental I have to substitute the value of modulus of elasticity. And since in the given problem for all the element, modulus of elasticity value is same, that is nothing but 29.5 into 10 to the power 6 Newton per meter square, divided by Le for the first element. We have already found out in the very first step, that is Le for the first element is how much? 40 meter. So 29.5 into 10 to the power 6 by 40 into LM. Already we have found out the values of L and M for element number 1 in very first step. So just substitute it, minus 1 0 1 0 into, that is nodal displacement vector. So if I see element number 1, I know that element number 1 connectivity is from 1 to 2. So if connectivity for element number 1 is from 1 to 2, then that Q matrix will be Q1 Q2 Q3 Q4. See, this Q matrix is Q1, Q2, Q3, Q4. Now we know each and everything. We know all the values of Q. Just substitute it, multiply the matrix. Finally, you will get the elemental stiffness matrix for the first element, which is coming out to be 20,000 Newton per meter square. Any doubt? कोई doubt है किसी को?
No, sir.
Okay. So similarly, in the same manner, we can find out the elemental stiffness matrix for the remaining element. So for one more element, I will show you. For second element, the matrix equation for finding out the stress is the same. That is E suffix small e by L suffix small e minus L minus M L M into Q matrix. Capital E suffix small e is same for all the truss member, that is 29.5 into 10 to the power 6 divided by Le. So from the very first table I have to find out what is the equivalent length of the second element. So I can see that equivalent length for the second element is how much? That is 30. So this value is 30, this value is 30 into, now I have to substitute in place of this lm as values of lm for the second element. So if I go back to the table, so for second element L is 0, M is minus 1, so you can substitute in that matrix. Okay, that is 0 1 0 minus 1 into this displacement vector matrix. So for element number 2, firstly I have to check the element connectivity. I can see that element connectivity is from third node to second node, from third node to second node. That means I am going from node number 3 to node number sorry, this is that yes, third node to second node. That means I am going starting from node number 3 and I am going till node number 2. So the displacement vector matrix will be what? It will be q5 q6 q3 q4, that is 4 cross 1 matrix. Check. that is q5, q6, q3, q4. Now you know all the values of q4, q3, q6, q5. Just substitute in that particular matrix, multiply the matrix, and you will get the elemental stiffness matrix for the second element, which is coming out to be minus 21880 Newton per meter square. And what does this minus sign indicates? This minus sign indicates that the second element will be subjected to compressive stress due to application of nodal forces. Likewise, in similar manner, you can find out the elemental stiffness matrix for third element as well as for fourth element. Is it clear? Any doubt?
No, sir.
Okay. So, and next, that is the last part of the problem is you need to find out what? That is, you need to find out the reaction forces. You need to find out what? Reaction forces. Okay. So, yes. So, if I see the diagram, if I see the diagram, I will get, if I see the diagram and if I want to draw the free body diagram of this truss member, I can say that I will get one reaction force over here, I will get one reaction force over here, I will get one reaction force over here, I will get one reaction force in this direction due to this fixed support, as well as I will get one reaction force in this direction. Yes or no?
Yes, sir.
Fine. So that means I want to find out the values of R1, R2, R7, R8, and I think R6. Yes or no? I want to find out. I want to find out the values of R1, R2, R8, R7, and R4. Yes or no? Yes or no? Hello.
Yes.
Fine. The remaining reaction in the remaining node, that means this particular value, this there will be no R3. I will not take this. There will be no R5. There will be no R6. Yes or no?
Yes,
Hello.
sir.
So if those reaction values are not present, I have to eliminate that particular row again from my original stiffness matrix equation. Then only I can use the elimination approach. Fine. So what we are doing, we are eliminating R3, R5 and R6. That means that value is nothing but equal to 0. There will be no reaction forces. That means this R3, yes, that is R3, R5, R6. There will be no reaction forces. So values of R3, R5 and R6 is 0. Values of R3, R5 and R6 is 0. Corresponding row, that is the third row, fifth row and sixth row, I have to delete it since there is no R3, R5 and R6 because LHS is equal to RHS. If RHS is equal to 0, there is no need to keep that particular row. So I from that stiffness matrix equation, which equation? That is F is equal to K into delta, where K is your 8 by 8 matrix, delta is nothing but Q matrix, 8 cross 1 matrix, and F is your again 8 cross 1 matrix. You have to delete the third, fifth, and sixth row. Fine. So on deleting or after deleting the third, fifth, and sixth row from the global stiffness matrix, this is the final stiffness matrix you are left out with. Into this value is what? This is your global displacement vector matrix, which is nothing but q1, q2, q3, likewise q8, and is equal to reaction. that is force vector here. Now this time the force vector will be nothing but the reaction vector, and since we have eliminated third, fifth and sixth row, so there will be no reaction force present. So that will be R1, R2, R4, R7 and R8. Now just solve this matrix equation very carefully. Once you solve it, you can get the values of reaction forces R1, R2, R4, R7 and R8. That is, R1 is coming out to be minus 15,833 Newton. And what does this R1 minus sign indicate? This minus sign indicates that I have assumed in my analysis the direction of reaction force to be wrong. Its direction will be in opposite direction. Similarly, R2 is coming out to be 3126 Newton. R4 is coming out to be 21879 Newton. R7 is minus 4167 Newton. That means the assumed direction of R7, which I have assumed by myself, is wrong. Its direction will be in opposite direction. And finally, the R8 value is coming out to be 0. So these are the reaction forces that will be acting at each of the nodal point due to application of external load on the joint member of the truss member. So this is the complete finite element modeling and analysis of a truss member. I hope this problem is clear to you. Any doubt?
No, sir.
Okay. So you can expect such kind of problems in exam. But again, I am telling you, okay, just wait. Let me stop the recording part. We are done with the class.